Okay, so yeah, let's begin with interpolation. So first of all, I would like to start with what is interpolation? What is interpolation? So suppose let us make this definition more formal. Suppose you have these data points. Okay, suppose you have the data points. These are the data points you collected after a survey. These are the data points you collected after a survey. Like, can you give me an example? Like, yes, maybe one example can be yes, sales of banana chips. Okay, so sales of banana chips. So this is the location. Okay, it is what is this area called? Palipuram, right? Mangalapuram. Mangalapuram. So this is Mangalapuram. Okay, so just short. And here you can let me make the sales big actually. Okay. Why I make it big? Because there are students here and they might like eating banana chips. So nearby university, if someone sells banana chips, it will go at a high rate sales. Okay. And these are at a deserted place, like where no one is mostly there. So still the rate is fluctuating. Okay. Because someone can bring the banana chips from there to someone here who is at the university. Okay. So like that, some sales can increase. So we cannot predict it, but you can see that now you have a strong intention to connect these dots, isn't it? You want these dots to be connected, right? But yeah, let's not worry about it. Now suppose you have these data points. How can I mark these data points? I can mark it A, B, C, D, E. But if you have 1,000 set of data points, you will run out of alphabets. Okay, so one good way is to make a notation. One good way is to make a notation so that you know which data point it is. And one good way to make a notation is write it as xi, yi. Isn't it? Write the data points as xi, yi, then you will never run out of notations. You can even write 10,000 sets of data, million sets of data, because numbers are endless. Okay, but alphabets are not. Okay, so this is the motivation which no one usually tells. Suddenly they start with, let us now write this as xi, yi, but why we can't? Number is a, b, c, d. Yeah, so now you got why we can't. Okay, so say this one was x1, y1, this one is x2, y2, x3, y3, and so on. You have a set of data points, so on, these data points. Okay, fine. Now the idea is what happens, what happens if Mangalapuram, this is a Technopark phase 1. Okay, in between that there are shops. In between that there are shops, and it is a bit predictable that the value, like, you cannot predict the value. It can be here above than that or below than that. We cannot predict. Okay, so therefore, like, how can you predict such values? Just have a rough idea, like how can the sales go for anyone who is in between Mangalapuram to Technopark phase 1. Okay, like in between that distance, if some shops are there, how much the sales can grow? You got the idea, right? So therefore, to do this, you use the technique of interpolation to find the sales in between the shops, like shops who are lying in between Mangalapuram and Technopark phase. Okay, so this is the idea. We will learn about the techniques, how you do it, but I will write you, like, it has to see. You have to approximate a continuous function. You have to approximate a continuous function which passes through all of these data points. That is the first criteria. Okay, else it is not an interpolating polynomial or interpolating function. Okay, it has to, if you are constructing an interpolation or interpolating function or interpolating polynomial, it has to pass through all of these points, all of your data points. That means it has to satisfy those points, right? That's the basic idea. So it can be like, I can start from here, yes, then it can go from, like, yes, it can go like this, like this. So this seems to be like a proper, like, I missed one. So it can pass like this, then it has to drop, then again it has to increase, and so on. Got the idea? So this is how non-linear the sales are. Okay, this is not a linear function. This is not a function like this. Okay, so it is a highly nonlinear function, and since it is nonlinear, it is not predictable by mind. Okay, if it is linear, it is easily predictable. If it is linear, it is easily predictable, isn't it? So since this is non-linear, it is a bit hard to predict. Okay, that's where we need the technique of interpolation. All right. So we will see a Python code for that, but we'll see something known as linear interpolation first. This is the simplest interpolation one can do. Yes. So let us see, like in linear interpolation, you have some data points. Say this is our uh, X and Y. Okay, this is our X and Y. This is our X and Y you have. And you have this Xi, Yi points. Okay, X1, Y1. And you have another point, say X2, Y2. These are the two data points you have. And your aim is to find what happens to a point which is in between, say here, okay, in between here. Say this is X star or maybe X cap, Y cap. You want to find what is Y cap at that X cap. Can you find? You don't know, right? You don't know because you only are given with these 2 points A and B. You don't know what is the value of Y cap at in between A and B. You don't know. So one simplest example is to do a linear interpolation, because from this graph it is visible to you, it is intuitive to you that you can just draw a straight line and that guy can just lie on that line. That middle guy, that is X cap, Y cap, can just lie on that line. Okay, if it was like this, then of course it cannot be a linear interpolation, because you know that you have to connect something like this, like a parabola or something. Okay, so this is the case. Yeah, so therefore we will take a linear interpolation first as the simplest example. So how we can find it? Can anyone tell? See, if it is lying on a straight line, the slope is the same, right? The slope is the same. The slope, how you find the slope if you are given 2 points? Yes, yes. So we just have to use that formula to find what is y cap given x cap. So you have to write y cap equals to something. That is our aim in this topic. Okay, how we do that? So you have to see that in order to do less work, what you have to do? In order to do less work, there is easy chance that you go inefficient in this also. So take the slope in between A and B. Okay, what is that? Slope in between A and B, like y2 minus y1. Yes, that is the slope, right? And that should be equal to the slope between A and C, or C and B also, right? The points between A and C and B. Yes, is it clear? So which one we should take? You take either one, you are in profit, right? Because there is always one known guy and one unknown guy. So you can easily write. So can you tell me, like, which one we should consider? Suppose A and C. Suppose A and C. So what should it be? Y cap minus y. Yes. Okay. Now can you tell me what is y cap? What is y cap? So you just have to take y2 minus y1 by x2 minus x1. All these are known quantities. You multiply, cross multiply, and this is known to you, this is known to you. Okay, x cap is known to you. Okay, then plus y1, isn't it? That's it. That's it. This is the simplest linear interpolation. Okay, given you have these known points y2, y1, x2, x1, x cap you also know where you want to find y cap, and x1 also you know, y1 also you know. So you can know what is y cap. All right. Understood this logic? We just equated that the slopes are equal. Okay, so we will just see a Python implementation of this. Okay, and we'll plot it. Okay, so let's see what's the Python implementation for this. Um, yes, so you can see it here. Um, what it says is you have to find the linear interpolation at x equals to 1.5 based on the data 0, 1, 2 and y is 1, 3, 2. Okay, can you write this down? Can you write this down? Like the data points x equals to 0, 1, 2 and y equals to 1, 3, 2. You have to tell me. Okay, let us consider this example and then later we can come to the Python code. Can anyone tell me what's the data? X equals to? Y equals to? And you want to find what is y at 1.5, at x equals to 1.5. Okay, y is a function of x. So I'm thinking like y at 1.5. What is the value of y at x equal to 1.5? So what you have? So you have, instead of 2 points, you have 3 points actually here. So what are these points? X equals to 0. And then at x equals to 0, you have y equals to 1. At x equals to 1, you have y equals to? Yes. Let us consider 3 here. So you have 3 here. Okay. This is 1 point. This is 1 point. At x equals to 2, you have y equals to 2. Is it the correct data? Did you tell me correctly, right? Okay. At x equals to 2, you have? Yes. Yes, so you have these 3 data points. Now, what he is asking in the question, he is asking what is the value of y at x equals to 1.5, where 1.5 should lie? In between 1 and 2, right? Yes, so in between 1 and 2, 1.5 should lie. And you want to estimate what is the y value. So, for which points you have to take for interpolation? Yes, you have to just take the points between 1 to 2. You don't have to worry about 0 to 1 because that point is not lying there. Okay, so just estimate what is this value. What is this value by joining it as a straight line and see like this is 1 point and this is second point and just apply this formula you have. And let me know what is y at 1.5. After that, we'll see that in Python. Yes. So I hope you got 2.5. Yes. And that's what I have done here. Like we have done here. You can see that I'm using that interpolate, scipy.interpolate. I'm importing something known as interpld. Okay. So this is, you have to import like this if you are considering interpolating functions or you want to construct something related to interpolation. And as usual, you import pyplot as PLT because you are plotting something. I think you will learn about more about this in your data analytics. Okay, that like when you can use, you even use the styles like the Seaborn poster and many other things. But Seaborn poster is already removed, like it's depreciated, not more anymore considered now. And this here I have given 2 arrays x and y, which is your data points, which is just your data points. So you can know if you want to scale this problem up, what you have to do. If you have 1,000 sets of points, you have to enter it as 1,000 sets of points in that array. Yes. So I'm just giving you a small scale example, which you can also scale it. Then f is equals to interpld x comma y. Okay. So you don't have to do anything else. Like no writing of that formula. It's already there. It's already there. So you just pass into that function the function x and y, the x data and y data. Fine with you? Any issues? Hmm? And then you ask, since you store that result of inter-PLD x comma y in F, isn't it? In F. So you can ask to F, what is the value of F at 1.5? Isn't it? Got the logic behind? You are storing that interpolating polynomial, all that information in F, because F equals to inter P1D, right? What is F? Yes. So you have whatever information related to that interpolation, all the things in F. Now, if you want to ask the question, what is the value of that polynomial at 1.5? Okay, you have to ask to F. Okay, so you are asking F in the F of 1.5. Okay, so what is y hat? I have named it y hat at one F of 1.5, and it is giving this value. You can see here 2.5. It is printing here. Okay, print y hat, printing here. Then we want to visualize this. So therefore, I am trying to plot this figure. Okay. Try to understand what this means. PLT dot figure fixed size equals to 10,8. What does it mean? Something 10,8 means in a figure you have both the horizontal and the vertical axis, right? The width and the height. Okay, so try to see what does this mean. Try to change this number and see how this plot varies. Okay, how the plot shrinks or scales up. Okay, try to play around these values. So I'll share the code, but that doesn't mean that you keep that code in your lab. Okay, try to vary some numbers, try to play around with that and see what is happening. Like that only you will get. Okay, try to do this without looking into the code. Okay, try to do this without looking into the code, and then you will realize that yes, what I'm missing, what I need to understand more in the code. Okay, please try to do this. Okay, else it will be coding has to be your effort actually. Coding needs to be the effort from your side. See, I will give you the code, but you have to see what you are like, where you are at that point, right? Then only you can refer to this code and take yourself forward. That is the basic step. Take yourself forward in this. Okay, all the materials are there more than ever. You just have to understand yourself and take it forward. That's it. Okay, anyway, so what we are doing, plot x comma y, fine. Okay. Yeah, then I'm plotting this 1.5 comma y hat. 1.5 comma y hat. So where is 1.5? I think that is the red point. Yes, you can see that red point here, 1.5. Yes. I think I can do control minus, right, to make it. So now you can see at least in one figure. So at 1.5, you can easily see these are the blue points where the data points given to us. And after interpolation, you got this line. Okay. And you are asking what is the value at 1.5, and it is giving yes, 2.5. Okay. Since this is a linear interpolation, you can easily see that the value of y was lying in between the value here and the value here. It did not go anywhere other than that value. Okay, nowhere other than that value it went. It lied in between those 2 points. Okay, that's what is a linear interpolation. So yeah, that's it. Other polynomials we'll see in the due course. Okay, so this is linear interpolation. Fine. Now let's discuss something known as a polynomial interpolation. This is another type of interpolation. So polynomial interpolation means you try to you interpolate a polynomial in between the given set of data points. That should be your aim. Okay, instead of the linear one, which was the previous case, now you use the polynomials to approximate your data. Okay, this can be an important question. Okay, what is the difference? You know about regression, basics about regression, right? Yes, no, no, some regression basics. So I want to ask this question. What is the difference between interpolation and regression? Okay, what is the difference between interpolation and regression? This is important, but we will not cover regression in this course. Okay, we will cover least square regression. We will cover pseudo inverse. What is the role of pseudo inverse? we will consider multilayer perceptron, what is the use of artificial neural network in regression and how it can be achieved and how it can be used in regression. All that in your next semester in numerical methods. Okay. I don't want to pack this by taking regression in this course. So I taught your senior members also to in numerical methods. I taught what is least square regression, what is simple regression, what is what you call how to find the regression using pseudo inverse, which is one of the most important one. Okay, pseudo inverse is one of the most important concepts. Pseudo inverse is already implemented in Python with just a function. Okay, so we have to understand that and how you can use regression using artificial neural network. Okay, like multi-layer perceptron is there, MLP. How using that you can do regression problems. Okay, so all this will be covered if I'll be taking numerical methods. If okay, there can be some other also. We don't. Okay. Okay, let's come to our problem. Polynomial interpolation. Okay. So we have again the problem is we have a set of data points. Okay, so let's have a data point. So this is these are the set of data points. I won't mark all of them, but just treat this as some xi yi, and this final one you can consider as xn yn. This final one you can consider it to be xn yn. Okay. Now our job is to find an approximate polynomial which fits this data. Okay, data points. So you can see that one good approximation would be I think it is, yeah, it is the yes. So this is the interpolating polynomial for your case. It is not smooth, which is wrong in my case, but the polynomial should be smooth. The polynomial should be smooth. Okay. But here you can see that it is not that smooth, but it's human-made error. But in reality, you can see. So what we are considering here is we want to find a polynomial passing through these xi's, yi's. These are your data points, and from I equals to 0 to n. Yes, these are all your data points. Yes. And how it will look like, since it's a polynomial, it will look like something like what the polynomial has, some constant a naught, then a1, some linear term, then a2x square, so on, right? A3x cube, like some, these are all the polynomials you are taking, right? Isn't it? Fine. And then how much we can go? So you will see that you can actually go till n, 0 to n. Okay, we'll see that. So this, how can you write this in a closed form notation? Can you write this in a closed form notation? Like, you don't have to write such a big thing. How you can write it? Yes, summation. Maybe let us keep it j, because I want to use I for some good use. Aj x power j, isn't it? Yes, and j is going from 0 to n. Agreed? So this is your interpolating polynomial. Okay. Now, if you want to find yi, what is yi? Yi is y at xi, that is equals to summation. Just substitute in place of x as xi. That's it. What is this y? This y is a function of x, isn't it? This y is just a y as a function of x, It's just that we are not writing it, but y is a function of x, and that is a summation of this. And we are interested in what is the value of y at xi. Then just instead of x, you just substitute xi. Aj, this should be instead of x, you substitute xi. And yes, there is a power of j here. Nothing else. I just substituted x equals to xi here. Okay with you so far? Okay. Okay with you. How many points are there by the way? How many data points are there? How many data points are there? Quick, you have 15 for 5 seconds. What are the number of data points? This you can consider as an aptitude question also. How many data points are there? Quick. Huh? No, think properly. Think properly. How many data points are there? Last. How many data points are there? Like we have how many data points? I have marked it. I have already marked it. Yes, it is n plus 1, right? Why? Because it is starting from x0. This is one good aptitude question. If you start from index 1 to n, then you have n points. If instead you start from 0 to n, it should be n plus 1 points. Okay, so suddenly this is a very good aptitude question. So mind me that in this course, you are learning some techniques and all these things, but you are also using your mind. You are also using your neuron cells and brain cells to understand things. Okay, which will be very useful in your aptitudes, building up your aptitude and also for your interviews. Okay. All right. So consider. So therefore, I can write consider n plus 1 discrete points. The discrete set of points because they are spread out. They are not continuous set of points. They're discrete set of points. They can be equidistant. They can be non-uniformly spaced out also. Okay. Do you think these points are uniformly spaced? Doesn't look like that, right? Because the distance between this and this less than distance between this and this points. Okay, the x points. So they are non-uniformly spaced. So it can be uniformly spaced, can be non-uniformly spaced. But we will make a very important conclusion towards the end of this class. Okay, what we need. Sorry. Yes. So is it good to have uniformly spaced or non-uniformly spaced? Huh? No. We'll see it is the opposite. Okay. So this is the non-intuition I tell you about. Okay. You will see why it is the case. Okay, consider n plus 1 discrete points. And those points are xi, yi from I equals to 0 to n. Fine. And what we want to do? What is our wish? We wish to fit an nth degree polynomial. Okay, that is y equals to say some pnx. Okay, that is this which I had just written. That is a0 plus a1x. Okay, so on till an x to the power n. Fine. Which passes through all these points, isn't it? So what you already have and what you want to find. So if you want to find this polynomial, what you have to find? Suppose you want to find this polynomial Pnx, that is the nth degree polynomial. You already know if you have n plus 1 set of discrete points, you can fit a nth degree polynomial. Got the idea? If you have 4 points, you can fit a third degree polynomial. Okay, got the idea? Yes. Now I am asking you, if you want to find the polynomial, what you have to find? What you have to find so that you can say that, yeah, I found that polynomial. Think. We are going step by step. I am trying to make you think instead of just writing it. So suppose you want to find the polynomial. If you want to find the polynomial, what you have to find? You have to find. Just this will shift the whole idea and lead us directly to the solution. If you could answer this, what we have to find? What you know and what you don't know. Think about it. What you don't know. What? Huh? Which? Which are the constant? Yes, exactly. Exactly. You don't know the constants a0, a1 up to an. Yes. Those constants, if you know, you already know the polynomial, right? And those constants a0, a1 up to an should depend on your data points, isn't it? Depend on your data point. It might be that data points are like this, then your interpolating polynomial is totally different, isn't it? So your constants a0, a1 up to an should depend on your data points, given data points. Okay. Now, how we can make a bridge between these two? You know what you want to find. You want to find the constants a0, a1 up to an, and you already know that it depends. If you want to wish to find them, then it should depend on the data points. Now, these two are two separate things now to you. How you can make a path in between them so that you can achieve that? Yeah. So, how we can do it? Okay, I will tell you one thing. You can use the fact that the given data point, you know the x coordinate and y coordinate, right? And the polynomial should pass through that, right? So it should satisfy that polynomial. So you can write it, right? So can you, for what you write? What you can write? Say you start from x naught, y naught. Substitute x naught, y naught here. So instead of the left hand side, you put y naught. And the right hand side becomes a naught plus a1 x naught plus so on plus an x naught to the power n, isn't it? Similarly, you have y1 equals to a naught plus a1 x1, so on till an x to the power x1 to the power n, so on. You will have yn, the last point, yn equals to a naught plus a1 x n. Yes, the more properly you say, the more understanding you are. If you're not saying it, you are lagging in some parts. You have to say it. Okay. An xn to the power n. Now you already know that you can write this in some other way, isn't it? What reminds you? How you can, shall you type all this in your computer? It is a bit hard, isn't it? How you can effectively write this in the matrix? Yes, exactly. You already know that a naught, a1 up to an are the unknowns. If you can write this in the form of ax equal to b. So you're coming again to your second unit. Okay. Can you write this? Let me know. How you can write this? Think about it. How can I write this in the form of two different matrices? See, you want the unknowns. The unknowns should be the x, right? Ax equals to b. They should be a naught, a1, a2, so on up to an. And there should be something on the right hand side. There should be something on the right hand side. Now you have to determine what is the left hand side, what is the right hand side. Right hand side is easy, isn't it? Right hand side is just y0, y1, y2, so on till yn. Then what is the left hand side matrix? Yes, you have someone is telling 1, then x naught then, okay. Second row, are you sure one will be there every time? I think yes. Then x1, okay. So until great. So now you know this matrix. Now great. Now you know the matrix. So suddenly you saw from one idea how we are representing going to linear equation, and suddenly we came up with a linear equation of ax equal to b form. Okay. Now you can just the above is a linear system which may be solved for AI to calculate the unknowns. Okay, you can use your previous known methods to find this. And this coefficient matrix, which you see just right on the left here, is something special. This matrix is something special, and it has a specific structure, isn't it? All ones in the first column, and then it is repeating. It is power is increasing by 1. Yes. So this special matrix is known as the Vandermonde matrix. This is a special matrix. Okay. Vandermonde matrix. It has a lot of different properties, and you can show that I told you in the system of linear equations, this system will have unique solution if determinant of that coefficient matrix is not 0. Okay, if determinant of this matrix, Vandermonde matrix, if it is not 0, then you will have a unique set of solutions to this system of equation Ax equal to b. Okay. So what is the determinant of this Vandermonde matrix? If you know, it is easier to calculate actually. What you can do, you can use some row operations and get one other rows to be zeros. Okay. And if you know if you have one set of rows to be zeros and one element to be 1, then determinant is only depending on that non-zero quantity. Okay. So I will leave that to you to find out, but let's not worry much about it. You can find out, but I'll just write what is the determinant of V is. This, let us say it is the matrix V for Vandermonde. So determinant of V, you can easily see, like after, like you can try a bit, not intuitive, not that intuitive. Okay, you have to do some operations and work on it. Okay, so you will get it as, any ideas, any thoughts before I write it down? Try to spend 1 minute thinking what can be the determinant, just by looking into it, like just by rolling your eyes and thinking what it can be. So it should look like something like this. Sorry, this is j, this is I. We have to follow the notations. Xj minus xi. Okay, it is the product of these xj minus xi's. Okay, and this guy is not equal to 0 because why it cannot be 0? Can you understand why? Just by looking into this, you can say no, it cannot be 0. Just by looking into this and using some common sense. What are xi's and xj's? They are the data points. They are the data points, right? They can never collide, right? You can never take the same point twice. They are all set of distinct points. Okay. Here we took the data points. They are always distinct. So since they are always distinct, the difference cannot be 0. Okay. Fine. Okay. So therefore, like since determinant is not 0, determinant of a matrix is not 0, that matrix is invertible. Like you can find the inverse of the matrix. Okay, you can find the inverse of the matrix. One good way is, suppose you have Vx equals to B here in this case, then you can find X as V inverse B, right? V inverse B. So for that, V inverse should exist. And we just showed that this exists. V inverse exists because determinant is not 0. Okay. This is, I'm not going into detail because this has a lot of proof and theorems. Okay. But I'm just showing you the middle path, like the path in between. Like you compute the determinant and determinant looks like this and it is non-zero. Okay. So you can compute V inverse and B. Then you find the unknowns. Okay. But there is a trick. There is a trick. Okay. Let us say that after this X you calculate will be this. What is this X actually? What is this X? Huh? What is this X? Huh? Yeah, but what is that X? I don't want the expression, but what was X? Yes, X was A naught, A1 up to AN. These are the coefficients of your polynomial, right? So you can find this polynomial in a unique way. In a unique way. You can see, you just have V inverse and you, right? There is no other way X can be taking a different set of values. Like quadratic equation. Quadratic equation, you have two roots. You have two roots, okay? But here you have only one solution. X equals to V inverse B. V inverse is unique. B is given to you as a unique. So it should be just one vector, right? It cannot have two different solutions. So the solution is unique. And what does it mean to have the solution unique? What does it mean to have A naught, A1, A up to AN unique? It means that you have only a unique polynomial. Polynomial. There is no other polynomial that can fit this data. There is no other polynomial that can fit this data. The only polynomial is phi, that is P of X, Pn of X. That is the only polynomial. I meant to say that you cannot have a polynomial like this. That is the only unique polynomial. Okay. And this we have just proved that it is unique. Okay. That's the idea. Why we can't have that polynomial? About it. It will be disclosed during the end of the lecture. Why we can't? Just make sure that you see these oscillations. In the previous case, the red curve doesn't have that oscillations, but the blue curve I just drew has some oscillations. Okay, oscillation is a problem in interpolation problems. If you have oscillations, you are entering a regime of difficulties. So try as much as not to make interpolating polynomials oscillate. Okay, if you start making oscillation is a problem, isn't it? Suppose you are in a plane, suppose you are flying on an aeroplane, okay? Suppose from here to Bangalore you want to fly, okay? Or maybe Delhi or Punjab you want to fly, okay? Then what happens in the middle of the flight? You started hearing this oscillation, cut, 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 cut. Then suddenly your adrenaline will be high, right? Suddenly you will be thinking that something is wrong. So oscillations are problems, okay? So due to that oscillation, you feel that there is some discrepancies in the flight, like some parts are loose, therefore it is oscillating, and you are in danger. Okay, so that is a common fact, and the same applies here in this case. If your functions, if your interpolating polynomials are oscillating, you are entering the regime of problems. Okay, so try to avoid it. We'll see that in the last part of the lecture. Okay, so yes, okay. Now, I told you one thing very easily, and you also accepted that very easily. But I wanted you to say to me that no, sir, it is difficult. But you did not say it. So suppose, will you, how many data points you will have, do you think? Suppose you do a survey, how many data points do you think you will have? You might have, like in a normal survey, like if someone has done some projects with data and data points. Minimum is 1000, right? Minimum is 1000. Like you can have more than that actually. So you will have 1000 set of points minimum. Minimum 1000 points. So how from x naught y naught to how much you will have? X 999, y 999. Isn't it? These are the set of data points you have. Now, can you tell me what would be the size of the Vandermonde matrix for this? So we are fitting how many points? We are fitting 1000 points. We have 1000 points. So we will use a polynomial of degree, say 999, which will be very high degree polynomial. Okay, you can see these are the cases where interpolation, like polynomial interpolation fails. These are the cases where polynomial interpolation will fail. If you consider this y to the power 999 polynomial, this will have a lot of oscillations. The more degree you make the polynomial higher degree, the more oscillations it will have, isn't it? Isn't, don't you think? One good way to make you think is think about y equals to x square. It's like a parabola. What is y equals to x cube? It will look like this. Okay. So think like if you increase the polynomial, what happens to the shape? Keep on increasing. Okay. Anyway, so this is just an idea I gave. But you can easily think that the van der Waals matrix, the size will be yes, it's a 1000 cross 1000 matrix. And I told you that you, in order to compute the set of coefficient, you have to do x equal to v inverse b. So you have to compute the inverse of that 1000 cross 1000 matrix. But do you think that is so easy? So that is not easy. That is not that easy. Not easy. So therefore, this is a limitation of that method. So you cannot always invert your van der Waals matrix. So therefore, we need some other different interpolation ideas. And that's where two other interpolation ideas comes to picture, which I'm going to cover and are most important. They are known as Newton's divided formula, like Newton divided difference formula. And another is known as Lagrange interpolation. These are the two interpolation that emerged out of this limitation. Okay, we don't want to invert the matrix. Without inverting the matrix, you will see that you can easily compute the values. Okay, you will see that, and it is pretty easy. Just use the basic common sense, and it will be flowing easily. Okay. Now I will tell you one more disadvantage. Now this is the size. Now I will tell you one more disadvantage. If xi is approximately equals to xj, if xi is approximately equals to xj, what does it mean? That means that your set of data points are close to each other. The set of data points are close to each other. This set of data points I meant. Here I have taken very nicely. You could have asked me, like you should catch me at every point, but I'm escaping from you. So I have drawn very nicely different in a different location. You should ask me, sir, why don't you take some point nearby? That can be a real case, right? If you take the points close nearby, xi and xj are nearby, then what this matrix will look like? What this determinant will look like? This guy, xj minus xi, right? It will be extremely small quantity. If it is extremely small quantity, you are getting a vibe that it is getting non-invertible. You cannot invert matrix anymore, right? Because if xi is approximately equal to xj, this implies that determinant of v is approximately equal to 0. Yes, if it is approximately equal to 0, what does it mean? You cannot invert that matrix. Matrix v is not that invertible. So your formula x equals to v inverse b will fail in that case. Will not give you the accurate solutions. Okay. So from here, I will mark this in red because this is. So how we can go to the next step? If determinant v is approximately equal to 0, this raises question about invertibility. Okay. So this is the thing. Then if determinant v is close to 0, then if determinant v is close to 0, v is approaching a singular matrix. That is a non-invertible matrix kind of. Okay. Fine. So in such a case, the matrix V will behave in an unstable manner, okay? And in that case, if you make some error, because there is always some error when you collect data, yes? And a small error or noise in the matrix element of V could bring a large change in the matrix V inverse. This is in the notes, I will give it to you, okay? And this will impact the computations of your unknowns, that is A0 up to AN, okay? So therefore, if your data points are close to each other, polynomial interpolation will fail. Fine. So therefore, polynomial interpolation can be achieved without inverse of van der Waals matrix. Something known as interpolating polynomials can be used in that case, which we will uh, learn in the next phase. Those sort of interpolating polynomials are known as, the method is known as Newton's interpolating polynomial method. Okay, that is our next plan. But now you got the idea, like how we are developing new ideas and how we are showing when the method can work and when the method can fail. Okay, just by using just a bit of common sense. We are not using anything hi-fi till now, right? We are not using anything very complicated math. It's very simple math. So you can see you got 2 points where polynomial interpolation can fail. And this is something important. You can expect something here. Okay. So in your like final summative, there will be 3 sections. I don't know if you are aware. Are you aware? You are not aware of it. So yeah. So the idea is like you will have 3 sections. One section would be conceptual understanding. Okay, one section will be conceptual understanding. Section B will be something like a bit of middle understanding, like something somewhat in the middle toughness. Then section C will be application based. Okay, 3 sections we have. So you can expect these kind of questions in conceptual understanding. It can be asked to you like, what is the issue? What is the issue with, can you say issue or limitations of polynomial interpolation? Okay. And how you overcome it. You can expect something like this. So you can start giving examples. Like, yeah, if you can take a bigger matrix, you have a lot of data points, then computing V inverse is hard. And then you can say, yes, if data points are close to each other, then the determinant van der Waals matrix V is getting close to singular matrix, and computing X equals to V inverse B is going to be difficult. Okay. So, yeah. Tell you one more thing here. Okay. I think, yes. So, due to the limitations, no.